And for the next talk, we move from Cambridge, Massachusetts to Cambridge in the UK. Francesco Poli is about to speak about exploration patterns in spontaneous self-touch actions in infancy. So we also move from moving in space to like touching the own body. So give a warm applause for Francesco.
Yeah, the head is not actually as big as the hair. So it should work. Thanks. All right. So yeah, I will talk about exploration on a body, but I want to start with some previous work that I did, and I hope it becomes clear why, on exploration of the visual space. And this is boring in the lab experiment, but I think some of these things are very useful, especially computationally, to be translated in research on body exploration. And a very easy way of testing information seeking in infants is by controlling very well the amount of information that we give to the infants at any time point. So we can, for example, present them with sequences. Here it is, in which the target is in more likely to be, for example, here in the upper left, but it could also appear in other places. And so, given these four locations, A, B, C, and D, we can specify what the sequence is, and from the sequence we can specify probabilities. So starting from the assumption that each location is equally likely, we can then, so 25% each in this pie chart, we can then update probabilities and see that location A is the one that shows the target, so this becomes more likely, and we can really do this for every single trial, and there were multiple sequences. And once we've done that, if we take two consecutive distributions and compute the KL divergence between them, we can get a measure of the information gain. So how different the two distributions are, or said it in another way, how much new information the new stimulus gives. And this is, for example, for this sequence what we get. And then, of course, this is a way of getting what is the information that is contained in the environment, but we want to see if infants are at all sensitive to this information. So one way to do this is we can try to predict when infants disengage from the screen. Do they disengage according to the amount of information we present? And what we see is that, indeed, if the information gain is high, infants are very unlikely to look away. But as the information decreases, they become more and more likely to look away. And this was done after controlling for other things like passage of time or the overall predictability of the sequence. So this is the visual domain. But also in this conference, we were saying a lot about how the visual world is actually highly complex. Many things are happening at the same time. And actually, baby's vision is not that great. We were testing 8-month-old infants here, but if we think about younger infants, it might be harder to do similar tasks. And also, another important thing is the motor development is still ongoing. So also, for example, all the manipulation tasks are things that you can only do later on. But there is one thing that infants might be exploring from very early on, and instead of focusing on the outside world, we try to focus now on the body. And if we look at how babies explore their own body, we can see that they engage in self-touch actions. So, for example, they move their hand on a specific body location for some amount of time, then some other location after an touch interval, and then again some other location. And if we, what we have here is recordings from 4 infants longitudinally where there was a coding of where they were touching, for how long they were touching, and what was the interval between touches. So this is the data we have, and I think is very rich data, and we have to find a way to analyze this data. And I think the first idea we have is that it would be nice to show that the self-touch actions are not completely random, but rather there are some latent states that differ in their exploratory value. So what I mean is sometimes the infants are in a more exploratory state about their own body, sometimes they're not. And finally, if this is true, it also means that some states can give higher information gain about the body. So how do we go about this? Well, so we have these observations, and they are following each other in time, and they are rich. So we have multiple things like the location, the duration, the intertouch interval or pause, and these are the observable states. But what we actually want to do is trying to predict what is the hidden state that generates this observable state. So for example, when I'm in a more exploratory state, what kind of location, duration, and intertouch interval am I more likely to exhibit? So there is some hidden state that can predict this observable state. And of course, every single observable state has a hidden state. And crucially, the hidden states are also related to each other. So for example, if I'm in the state S1, or let's say higher exploration, I'm more likely to stay in state S1, but with some probability, I might switch to state S2. So what we actually just did, we just made a hidden Markov model that we can then fit to the data. And when we do that, we end up having, and we specify that we want to find two states, we end up having two states, and the idea is, can we find any differences between them? For example, can we see that one state is higher in entropy than the other? Where what it means is that when you are in a state, S1, it's harder to predict the kind of observations that you're going to see. It's a higher entropy state. It could also be that there is no difference whatsoever in entropy between the states. And what we see is that consistently across development, so this is from 6 weeks to up to more than 30, there is a significant difference in entropy between the two states that our model found. And interestingly also, if we look at this dashed gray line, this is completely random movements. So whatever is happening is also not completely random. And I think this is already interesting in itself, and it might answer a little bit the first 2 points here, that the self-touch actions are not random, and also that there are these two different latent states, and they differ in their level of entropy, which might be related to exploration and how much information they actually gain. But in order to answer that, we also wanted to actually measure the information gain of each body touch. And the way we do that is actually very similar to the first study I presented. There, the information was about locations on the screen. Now the locations are on the body. I'm presenting just, 5 locations here. There were actually 14. This is just easier to show. But we can track how much a single touch changes the distribution. And what it means is that the sequence of touches might be a novel sequence compared to before, and so a sequence that might be informative about the mapping between different body areas. And so if we plot the hidden states where 0 is a state with low entropy and 1 is a state with high entropy, across time, we have something like this, but now we have a richer picture of how much information was contained in each single touch. And what we can do now is ask, is there more information in the high entropy state? And if we plot that, so here we have on the y-axis the information gain, x-axis the age in weeks, and the two different colors for the two latent states. We can see that indeed the high entropy state corresponds to greater information gain about the body. But this, interestingly, is true only until about 24 weeks of age. And then this difference disappears. So there might be something unique about how very early in life infants are exploring their own body and are gathering information about it. Now, I think this is the key result. But now the key question is how intentional this is. I don't think we can answer this question with this data. There is more. We actually have way more data than just this. So I'm very excited to work more on this. We also have, for example, we saw Mimo that I think could give very, very interesting insights in this. And so I think we will get closer, especially in collaborations with robotics, to understanding how infants explore the environment around them, but also their own body. And with that, I can wrap up, and I want to thank my collaborators, and also thank you for the attention.
So, thank you, Francesco, for this interesting talk. And there's a question here in the to the left, in the middle. Okay.
Thank you very much. Very interesting. I wanted to ask you about the information gain. The mathematical model behind is frequency, basically, right? But it is at least likely that when touching the same location again, the quality is changing, right? So it is not about the frequency, but rather the accumulating information that might be changing in quality. Do you have some thoughts on that?
Yes, definitely. I think ours is a very first step to try to capture some of the information that is there. So we thought the easiest thing to do is transitions between different body areas. This was indeed frequencies, but we also tried with transitional probabilities, and we get very similar results. The complete picture is more complex, and this is definitely one thing we wanna look into. Also, some touches are complex in the sense that they're moving across the body. So we're not capturing that either. So there is definitely, the data set is so rich, we had to start somewhere, but we'll do much more.
Okay, other questions? Maybe we move up. Yeah, okay.
Hi, thanks for the very inspiring and interesting talk. I found it really interesting that you found these differences in entropy of the observed behavior. And since we know that from electroencephalography, you can also record neural activity and estimate entropy in terms of neural activity, do you think that this kind of co-registration with EEG could bring something into your theory? And do you think that it could be feasible to do this kind of analysis also exploiting neural data?
Oh, it's very interesting. I never thought about it. The type of analysis is definitely feasible on that data. I don't work with that data, so the usefulness of that would probably be on people that do, but I'm very happy to chat about it. It's very interesting.
Mm-hmm. Because the mic is up, right? Okay.
Yeah. Thanks, Francesco. Great talk. I have two questions. One is, how much do you try or intend to try to relate those states into an actual kinematics of how the body moves? What were the motor movements that preceded, that were before those specific events? There's one question. The second question is, self-touch is one aspect of getting information about yourself, but also, when they kick their leg and kick the floor and things like that, this is also information. Tactile information. Do you have any way to kind of analyze that or get this kind of data?
Yeah, thanks. No, that's a very good point. So about the first one, we will also have information about kinematics, so things like acceleration and deceleration. And I think that is very, very important also in relation to intentionality, because we know what are the specific types of movements that infants do when the touch is intentional. So one thing we can do, for example, is take these two hidden states and see if there is one where movements are more intentional than the other, or stuff like that. And I think that is one way to go. The other way is to actually use that data to improve the estimates of the two hidden states. And I think those are both possible things to do. And actually, it relates to the second question. I would probably do that. I would try to find a way to get an even richer data set to inform the hidden states, because the HiddenMarkov model is actually data hungry. So if we give more data, it's probably happy. So yeah.
Yeah, just to follow up on this. So I mean, following the previous talk, which had a really nice approach to take kind of a motor model and try to. So I think it will be quite interesting to get a kind of a model from motor control that can explain some of those movements, and then build this on the state that you're showing. Nice work, thanks.
Yeah.
Mm-hmm. Okay, so thanks again,
Thank you.
Francesco, for the presentation.